All right, thank you so much. So we are back from going through L'Hopital's rule. Now let's talk about a function of this form, right? So we saw that all the differentiation that we are doing is in the form of, let's say, explicit, like y is equal to a function in terms of x. But the question is, what if the function now is not in terms of only x, or it is not, explicit, and it is what, implicit? Example like this. Then how are we going to do the differentiation? So it means that we are going to talk about the implicit what, differentiation. I'll guide you with some things before we start solving questions on it, right? So what we need to learn from here is, now I'm just showing you something here. If I have x and I'm differentiating x, then I know that when I differentiate this, I'm going to have 1. And then when you differentiate y, what do you get? We know that we get y prime. How? It means that here the idea is that when I'm differentiating x, I'm differentiating it with respect to x. So it's kind of d over the x, and I'm differentiating x like this. So this is like dx over the x, and then it will cancel out. So this is going to give us 1. But here is like I'm differentiating the function with respect to x, but this is y. So this is going to give me dy over dx, and this is y prime. So basically, that is the implicit differentiation. What the idea behind this that we want to, do it. So now let's, focus on these two things together. Then we can start, solving more examples on this. So I want to differentiate x squared. What am I going to get? So we know that since I'm differentiating x squared with respect to x, then this is of course 2x. The same idea. But when I'm getting this 2x, the idea is that it's kind of like I'm using the change rule. So I need to, when I finish, I need to differentiate x. But this is going to give me 1. So you see that there is no need for me to bring this one. But let's look at when I'm differentiating y squared. When I'm differentiating y squared, what am I going to get? It's the same way of using the power rule of differentiating x to the power n. So this one too is going to give me 2y. But here I need to do something in addition to this. I'm going to multiply this one by dy over dx. Why? Because now when I differentiate the y squared, I need to multiply it by differentiating the y. So it's kind of like this, y squared. So let's use the change rule. This is kind of 2y, 2 minus 1 times, then I need to differentiate what is inside the parenthesis. And this is going to give me y prime. So this is going to give me 2y times y prime, which is like this one here. But if I'm using x squared, then this is 2 times x, 2 minus 1 times, I differentiate x. But this is going to give me 2x. When I differentiate x with respect to x, I get 1. So this is still giving me 2x. So please, when we are dealing with implicit differentiation and we are differentiating it with respect to x, anytime you differentiate y, when you finish, you need to multiply your answer with respect to dy over dx. So that is one key thing that you need to remember. Anytime I finish differentiating y, I need to multiply it by dy over dx, or we can say that you can multiply it by y prime. Now let's look at this. These are two functions, x and y. So this is kind of like, let me say, the product rule. So if I choose a to be x and b to be y, then the question is, when I differentiate a with respect to x, what am I going to get? 1, right? And we know that when we differentiate y, what do you get? Y prime, right? Good. So it means that using the product rule, I'll multiply this one by this and multiply this one by that. So this is going to give me xy prime plus x. Very simple. So with implicit differentiation, these are some of the things that we need to also have with them in mind. So the normal differentiation that we are doing, we are applying them the same thing here, but here is implicit. The idea is that we have y also inside. Now, another thing that we need to talk about is we want to talk about high order derivatives. So when we say high order derivative, you see that everything that we are doing was like, we do first derivative. We just differentiate the function just once and we are done. So in this video too, I'm going to help you to learn how to do high derivative. So if I have y to be this, then when I differentiate it for the first time, I'll have y prime. When I want to differentiate it again, and this is the same as dy over dx. When I want to differentiate it again, I have y prime prime, and this is the same as d squared y divided by dx squared. When I want to differentiate again, I have y prime prime prime, which is the same as d3, right? And when I want to differentiate again, this is like you can choose it to be y4, and this will be d4 y divided by x to the power 4. This one's supposed to be 3. This one here, you can write this one as y, let's say iv. It's also the same thing. So this is the like high order derivative. Like now we don't want to differentiate it just once, but we want to move further, like differentiating it more, right? So let's take some examples and then combine the idea of whatever we are learning from here. So use implicit differentiation to find dy over dx. So now let's go through this process. So implicit differentiation, what we just need to do is, if I have a function like this, I need to take d over dx on both sides of the function. So 5y plus x is equal to d over dx. So don't forget, the same rules is going to apply. The same rules, nothing is changing. So this is kind of like when I multiply them through, I'm going to have d over dx times xy squared plus 5 is constant, so I need to differentiate just y, then plus, now I differentiate x. Then we know that when I differentiate a constant, I get 0. So this is going to be a big 0 here. Now, what can we see here? This is a product rule, right? So as we've done a lot of product rule questions that goes with the product rule, find your A, find your B, and you do it. But this one, I'll do it straight. So since this one is a product rule, first I will maintain x. So when I maintain x, I need to differentiate y. So when I differentiate y squared, I'm going to have 2y times dy over dx. Don't forget, as I said, anytime you differentiate y, when you finish, you need to multiply it by dy dx, as we learned from there. That's what we just did, right? Then plus 5. And when I differentiate y, I get dy over dx, right? So that's what I'm going to get there. Plus, when I differentiate x with respect to x, I get 1. So this is equal to 0. So now what are we looking for? We are looking for dy over dx. So we need to just group like terms. Then we are done. So this is going to give us 2xy dy over dx plus 5 dy over dx. Then I'll send a 1 to this side, which is minus 1. Then what am I going to get here? I have dy over dx, dy over dx. I can factor it out. So this is going to give us 2x plus 5, which is equal to minus 1. Then since we want to get dy over dx, I need to divide through by this. And this is going to give us minus 1 divided by 2xy plus 5. So what are you seeing here? You see that since this is implicit, you see that always our final result is in terms of x and y. The one that we were just doing, we saw that always our answers are in terms of just x. You see that? So that is just the difference between the implicit and then the normal differentiation that we do. Let's take more example and then see how we can do this. Let's just differentiate this. So we are using the same idea, how to differentiate the functions. The same thing. Now, what are we going to do here? We want to differentiate this, right? Implicit. So I differentiate both sides. So cos xy plus sine x is equal to, I take the derivative of 10. So now let's differentiate this. Differentiating this, we need to use the change rule. So let me just pick them on it just one by one so that I can teach you very well how to do this. Cos xy plus I differentiate sine x, And then when I differentiate a constant, I get 0. So now let's see what we can do here. Now here I'm going to use the chain rule. So the chain rule says that first the derivative will hit what is here, right? So it means I'm going to have negative sine x xy times, then I differentiate what is inside the bracket, so times dy over the x xy, plus when I differentiate sine x with respect to x, I get cos x, and this is equal to 0. Now you see that now if I want to differentiate this is a product rule. So I need to apply the product rule to what I have there. So this is minus sine xy times, now I need to apply the product rule here. So I'll open my bracket. If I maintain x and I differentiate y with respect to x, I'm going to have dy over the x, plus, now I maintain y and differentiate x with respect to x, and I have 1 plus cos s is equal to 0. Or you can use the idea of picking your a and b, and I think we just did this one somewhere here when I was doing it, how to differentiate x times y. So you use the product rule and you get something like this. So that's basically what we are just trying to apply here. So now we are looking for dy over the x, so we are trying to make that one the subject. So before we make that one the subject, we need to multiply through by this. So I'm going to have something like um, I'm going to have something like this. Let me say minus sine. Let me see. So this is going to be minus sine x y x dy over the x, plus going to be minus again sine xy times y is equal to minus cos x. So multiply this one by this and that, and I move this one to the right. So since we are making this one the subject, this one is going to be minus sine xy x dy over the x is equal to, so I'll move this one to the right, becoming positive. So this one is going to be y sine xy. So when I move this one, become positive. Then minus, we have minus cos s here. Then for me to get this, I need to divide through by this guy. So now dy over the x will be equal to y sine xy minus cos x divided by minus x sine xy. So minus x sine xy. Yeah, so this is what I'm going to get. I think I can't do anything again, but I can just make sure that the minus here just get away. So I can pull minus out from here so that I have minus, then I have cos s minus y sine x y divided by minus x sine x y. So how did I do it? You see that when you multiply this one by this, you are going to get minus cos, and when you multiply this one by this, you get positive of that. So that I can cancel the minus out and have it to be cos x minus y sine xy divided by x sine xy. So this is what I'm going to get at the end of the day when you solve it. So it's just kind of, we need to practice, and it will be good. Now let's look at some of the high orders to example, right? So we are practicing. Now first, we are saying that x to the power 3 minus y to the power 3 is equal to 1. We want to show that this is true. Okay, so it means that we need to start from here. And since this one is having y prime prime, it means that we need to differentiate this one 2 times. So that's the first trick that we need to learn from here. So let's go x to the power 3 minus y to the power 3 is equal to 1. Let's use the implicit differentiation. So I differentiate both sides. X to the power 3 minus y to the power 3 is equal to 1 is equal to dy over the x 1. When I differentiate 3x with respect to x, I'm going to have 3x squared minus, when I differentiate y with respect to x, I mean y to the power 3 with respect to x, I'm going to have 3y squared, but don't forget to multiply by y prime. Good. And this is going to give us 0. Let's make y prime the subject. So here, I can move this one to this side or move this one to this side, right? So I'm going to have minus 3y squared times y prime is equal to minus 3x squared. I want to make y prime the subject. So y prime will be equal to minus 3x squared divided by minus 3y squared. This will cancel this, and this will be x squared divided by y squared. Now, since we've gotten y prime, but this one is in terms of y prime prime, so we need to differentiate again. So now we have y prime is equal to x squared divided by y squared. So guess which rule are we going to use? We need to use the quotient rule, right, to solve this. So using the quotient rule, it means that, let me just bring this guy here. It means that we need to pick our u. So u is x squared, then is y squared. Now the question is, what is u prime? When I differentiate x squared, I get 2x. Is that right? When I differentiate y squared with respect to x, I'm going to get 2y, but don't forget to multiply it by y prime. So you see that anytime I'm differentiating y, I multiply it by y prime. If it is the power is not, it's more than 1. But if I'm differentiating y, then it's just y prime. It's just y prime. But if the power is more than 1 and it's like 5, you follow the power rule, and when you finish, you multiply it by y prime. So that is what you need to also have it in mind. So now let's go. Using the quotient rule to do this one means that we are differentiating it again. So this is going to give us y prime prime will be equal to then u prime minus u then prime divided by then squared. So y prime prime is equal to then is y squared, u prime is 2x minus u is x squared, and then then prime is 2y y prime divided by then squared. So this is going to be y to the power 2 or to the power 2. So now, since this is in terms of y prime prime, we don't need to differentiate again. Now we need to try to simplify this to get what is there. So this is the same as y prime prime is equal to simplify this. This is 2x y squared minus this is 2x squared y prime divided by y to the power 4, right? So let's try and simplify this and then see how we can work with that. So let me just move these guys up here so that we can have a space to work with the thing that we are doing here. Good. So now let me just rule a line here so that I can pick it from there. So now that we've gotten this, I can multiply this one by this. So we are going to have something like y to the power 4 y prime prime, and this is going to give us equals to 2xy squared minus 2x squared y prime, right? So let's look at what we have here. So what we have here is like y prime prime y to the power. So we don't even have y prime inside, but here we have y prime inside. It means that we need to make sure that the y prime is not there. So what is y prime? We saw that y prime is equal to x squared over y squared. So we need to do substitution so that we get away from the y prime, because we don't have y prime in the final solution here. So this is the same as y prime prime times y to the power 4. I just interchanged it. And this is 2xy squared minus 2x squared y times. Now y prime is x squared over y squared. So this is going to be x squared over y squared. So let's try and simplify it from here and see if we are going to get a solution from there. So this is x squared y squared minus 1 of the y will cancel 1 of the y here. So I'm going to have 2x to the power 4 divided by y, right? So 1y cancel 1 of the y here, and then x squared times x squared will be this. So I'm going to multiply through by y. So when I do that, this will be y prime prime y to the power 5 is equal to When I multiply this one by y, I'm going to have like 2xy to the power 3, and then minus, when I multiply this one by y, this is going to be 2x to the power 4. So we've gotten this y prime prime y to the power 4, y to the power 5, but we see that we have 2x here. So let's try and factor 2x out since we have 2x, and let's see what we can get from there. So this is 5y is equal to, so when I factor 2x from here, I'm going to have y to the power 3 minus x to the power 3. Good. Now what can we do? We see that we have this one here. We have x to the power 3 minus y to the power 3 to be equal to 1. We know that x to the power 3 minus y to the power 3 is equal to 1. But this is y to the power 3 minus x to the power 3. So I can factor minus out so that it can help us to get what we are looking for. So this is y prime prime 5 to the power, y to the power 5 is equal to. When I factor minus out, I can switch this one as x to the power 3 minus y to the power 3. Then now this is equal to 1. So we are going to have y prime prime y to the power 5 is equal to minus 2x times 1. And this is the same as y prime prime y to the power 5 is equal to minus 2x. And this implies that y prime prime y to the power 5 plus 2x is equal to 0, which is indeed what you've gotten here. So this is high order derivative. Like, you do it and then you look at, as soon as you are doing it, when you see some question like this, the first thing that you need to think about is you need to think about look at the higher derivative inside. So you saw that this one was having 2-second derivative, like y prime prime. So we differentiated it up to y prime prime, and then we stopped and we started simplifying. Looking at the function, we saw that there was no y prime, so we need to change the y prime and replace it by the y prime that we had. And then when we got here to, we need to look at the original function, and then we need to do substitution to get what we have here. Now let's look at this one to find the second derivative of the following functions. So second derivative means that we need to differentiate the function 2 times. So let's see what's going to happen here. Let me pick a first. So a, I have y is equal to cos of the natural log of x. So what are we going to get? Y prime, this is change rule, right? So first, the differentiation will hit the cos. So it's going to give us minus sine x, and then we maintain what is inside. Then times, now I need to differentiate what is inside. So when I differentiate ln x, what am I going to get? I'm going to have 1 over x. So first, the derivative will hit cos, giving us minus sine of the function. Then when we are done, we differentiate what is inside there. So since we are finding the second derivative, let's try and simplify this and see what we are going to get. So this is the same as minus sine ln of x divided by x. So now that we want to go again, now the function now is now going to pick the quotient rule. So u and vin. So what is u? U is minus sine ln of x, and vin is equal to x. So what is vin prime? Vin prime is 1. And what is u prime? U prime, we need to use the change rule. When I differentiate cos, what am I going to get? Sorry, sine, what am I going to get? I'm going to get cos. So this is going to be minus cos ln of x. And when I finish, I need to differentiate what is inside, what is going to give us times 1 over x. So what will be y prime prime? Because we are differentiating it again. We are differentiating it again using the quotient rule. So this is vin u prime minus u vin prime divided by vin squared. So what is vin? Vin is x, u prime is minus cos ln of x times 1 over x, Then minus u is minus sine len of x times vn prime is 1, all divided by vn squared, which is squared here. So simplify this, and we are going to have, so x will cancel the x. So I'm going to have minus cos len of x minus, oh no, plus sine of len x divided by x squared. So this will be the second derivative of the first function that we were doing. I'll give you a trial question to do. So stay here with me. y is equal to ax x to the power a. Good. So this, if we can look at this well, you see that we have a lot of work to do. This is like constant base, and this is like the power rule, right? So we need to use product rule, right, for us to do this. So let me use the product rule by assigning big A and big B. So this is going to give us A is small a to the power x and B is x to the power small a. When I'm differentiating A, now remember A is the constant base, right? So it means that when I differentiate, I will differentiate the exponent, which is going to give us 1. I maintain the function, then I take ln of the base. Then this is going to simplify to ax ln of a. Then when I'm differentiating b, b is actually the power rule, right? So the power rule, a comes down, then a minus 1. The power rule is just like this one is not n. So this is what I'm going to get. So let's just multiply, and we get y prime. So this is going to give us, this times this is going to give us ax a x minus that plus this times that is going to give us x to the power a times a to the power x ln of a. So we need to differentiate it again. Now using indices, this is to the power 1, so I can combine this one together and write it as x plus 1 minus 1 plus this one. I cannot do anything like indices here, so x to the power this times x, and then I have ln of a. So we need to differentiate it again. So y prime prime, another product rule again, but remember this here is basically the same as this. Can you see that? A to the power x, 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 x to the power a, x to the power a. This is constant because there is no x. So it means that if I want to differentiate this again, I'm going to have the whole of this again multiplying ln a. So we know how to do this. So let's focus on this. Now focusing on this, what we just need to do is we need to pick another a. So let me pick a to be equal to a to the power x plus 1 and b to be equal to x to the power minus. Good. So the same idea with the constant base and then the power rule. A prime will be equal to, differentiate the top, you get 1. So when I differentiate x plus 1, I get 1. Then I maintain the function plus times the length of the base again. Then b prime now will be a minus 1. You drop it, and then x to the power a minus 2. Subtract 1, so you get something like that. So what we just need to do is multiply this one by this, multiply this one by that. So let's go through. When I multiply this one by this, I'm going to have ax plus 1 times a minus 1, x to the power a minus 2. I'm going to get something like a minus 2, and then I need to multiply this by this, and I'm going to have plus x to the power a minus 1 times x plus 1 times ln of a plus, now plus, I'm going to copy the whole of this. So I think I can paste it down here. Is it going to go there? No. So it's going to be plus the whole of this times ln of a, because If I take the lane of A to be here and I'm differentiating this, this is the same as this, and this is what gives us this. So this time the lane of A. So I think this will be the final results that we are going to get from this. Do you have another question that we need to try? Okay, let's go through this one too very quick. So here we want to find dy over dx, not dy over dy. This one should be x at the point 2 and 1. So let's go through quick. I have x squared y minus y cubed minus 6. So put x squared y minus y cubed d over dx minus 6. So what am I going to do? Use the product rule for this. So I maintain x squared, differentiate y, I get y prime, my plus maintain y, differentiate x squared, get 2x, minus differentiate y to the power 3, and we are going to have 3y squared times y prime. And when I differentiate a constant, I'll get 0. Now, one thing about this, whenever we are solving something like dy over dx, and we have a point here, is I can decide not to simplify and plug in just the point, knowing that this is x and this is y. So let's plug them in. We are going to have 2 squared y prime plus y is 1 times 2 times 2 minus 3 times y squared, and then this is equal to 0. So this is going to give us 4y prime plus this is going to give us 4 minus 3y prime is equal to 0. So see what we are going to get here. 4y prime minus 3y prime is going to give us y prime plus 4 is equal to 0, and y prime is equal to minus 4. And this is like y prime is the same as dy over dx, which is equal to minus 4. Now don't forget, anytime we have something like this, we call it slope. So this is the slope that we have calculated. Good. So that was the last example that we need to solve under implicit and high order. Giving you this example to also try. So try to find this and leave your final results in the comment section. So in the next video, we are going to talk about tangents and then normal to the curve. So we are going to talk about tangents, and then from there, we can talk about critical values, local extrema, and then other stuff that we need to talk about. So solve this one and leave your answer in the comment section. See you in the next video.